So in the last class, we have seen what is power of element, how to define power of element, what is subgroup. So these concepts we have seen, and this very important, subgroup generated by an element. Okay, so what is subgroup generated by some element A? So these concepts we have already seen. Now let's move on. So remember, this is very important concept. So that is the reason I am just writing it one more time. So if you have a group, okay, so if you have a, let's assume you have a group. So if you have any group G, okay, and there is some operation, this is some group operation star, then in this situation, what I will say that, okay, and let's assume you have any element, you can have any element belonging to G, then what this means? This means subgroup, this symbol means a subgroup generated by A. This means subgroup, this means subgroup of G generated by A. Okay, generated by A. So this is the idea. And what this is, what is the definition? Can anyone tell me? Subgroup generated, subgroup of G. Remember, this is subgroup of G. So this is the subgroup of G which is generated by A. Okay, and I can say this is the smallest subgroup which contains A. Another word is smallest subgroup of G that contains A. Smallest subgroup of G containing A. This is another definition, containing A. And finally, I can say this means all the integer powers of A. All the integer powers of A. So that will be your subgroup generated by A. Just take all the integer powers. Okay, very simple. Remember this definition. Don't forget this definition. This is subgroup. This is smallest subgroup of G. This is smallest subgroup of G that contains A. Okay, so this is the definition of subgroup generated by A. Now let's see some notation I just want to tell you. So this is the notation for subgroup. So for subgroup, this notation is sometimes used. So for example, if I say H is subgroup of G, then how to say this? If I say H is subgroup of G, then I will write it like this. H is a subgroup of G. Okay, H is a subgroup of G. So this is how people write sometimes. Okay, so this symbol people use, this is the symbol of subgroup. Okay, so this symbol means subgroup. Is this clear? And this symbol means subgroup generated by A. This symbol you already know. This means subgroup generated by A. So this is subgroup generated by A. This is subgroup generated by A. And another is, what is this? If you have any group, let's assume you have any group G, then what is this symbol? What is this symbol? So what is that? This means order of G. It simply means order of G, or that is number of elements of G. Basically that means cardinality of G. I can also say that is cardinality of G. This is simply cardinality of G, or I can say order of group. This is the order of group. Okay, so this is the, now remember, some people also write like this, some people write like this, some people write like this. So both are correct. Okay, so both are correct, and this simply means order of group G, order of group. And order of group G, that means number of elements in G, and this simply means number of elements in G, number of elements in G. Okay, so all these things are same. Now let's move on. Let's solve this question. Okay, so tell me what will be the answer. Think about it and tell me. So if G is a group, this is a very simple question. If G is a group and A belongs to G and A is inverse of itself, then what is the subgroup generated by A? So what will be the answer for this? Remember, A is inverse of itself. A is inverse of itself. What it means? Can anyone tell me what it means? A is inverse of itself. Okay, then what is the subgroup generated by A? This is given to you that A is inverse of itself. Does it mean identity element? This is my question. Tell me, does it mean identity element? This is my question. Okay, tell me. If you have a group, okay, and let's assume that let's assume you have A belonging to G such that A inverse is equal to E, then does it mean A equal to identity element? Then A is identity element. Can I say? It need not be identity element. Okay, the answer is no. The answer is no. See, for identity element, this will happen. Okay, remember, for identity element, if you have identity element, this will happen. That E inverse is equal to E, this will happen. But if this is happening, but if A is equal to A inverse, that does not imply that A is equal to E. That does not imply. You can very easily take this example. For example, consider this. Do you remember in the last class we have taken this 1, 3, 5, 7. Consider this group multiplication modulo 8. Consider this group. What is this group? This group is known as, what is the symbol for this group? Can anyone tell me? What is the symbol for this group? That is U8, right? Do you remember U8? This is your U8. Okay, now here you can notice this is the identity element. So identity element always inverse will always, so 1 inverse will be 1. But what is 3 inverse? Tell me what is 3 inverse here? Here 3 inverse is 3. Here 5 inverse is 5. And here 7 inverse is 7. 3 inverse is 3, 5 inverse is 5, 7 inverse is 7. So you can clearly see that 5 inverse is 5. That does not mean that 5 is identity element, right? Yes or no? Agree or not? So if A is equal to A inverse, it does not mean that A is equal to identity element. But if A is identity element, then it will be inverse of itself. Okay, so let's move on now. Now tell me about this. So if A is, this information is given to you. Now tell me what will be this. This will be A power 0. Okay, let's see one by one. This will be A power 0. What is A power 0? Anyone want to tell me what is A power 0? That is always identity element. That is always identity element. You don't have to think about it. This will always be identity element. And what will be A power 1? That will be A. What will be A power? What will be A inverse? What will be A inverse? That also will be A. What will be A square? Remember, A is inverse of itself. Remember, A is equal to, so A square means A star A. And remember, A is equal to A inverse. Remember, A is equal to A inverse. So A square will be E. Okay, yes or no? So this idea, very simple, because here you can notice, for example, what will be 3 square? 3 square will be 3. Okay, and this you can notice that, what is this? So that will be 1. You can notice this is your identity element. So because if A is inverse of A, then you can very easily see that if A is equal to A inverse, then what will happen to A square? A square will be this, and because this A is equal to A inverse, you already know, so I can call it, so this will be A square will be E. So that is the idea. Okay, so you can just apply this. A square also will be E. A cube also will be E. And what will be A power minus 2? What will be A power minus 2? That also will be E. A power minus 3 will also be E. So what is the, tell me, what is the group generated? What is the subgroup generated by A? So finally, you can say that if you have a group, and in this group, let's assume that you have some elements such that A inverse is equal to A. Okay, remember this means, this simply means that A power n is always equal to, I can say, this means that A power 2 is equal to A, E. And A power minus 2, what that will be? Just think about it. What will be A power minus 2? A power minus 2. That means A inverse power 2. A inverse is A, so that is A power 2. And A power 2 is E, so this is also E. A cube will be A, right? So sorry, A cube will be A. Sorry for that. A cube will be A. A cube will be A. Okay, so just take care, because what will be A cube? A cube will be A square dot A. and you know what is a square. This is e dot a, that is a. Okay, so this is the idea. For example, a power minus 3, that will be a inverse power 3, and that is a inverse is same as a inverse is same as a, so this will be simply a. So that is the final idea that I can say, and this is important. So just like these questions are very simple. Can you notice, if this question comes in the test series or gate exam, then this is a very simple question. This is given to you, a is inverse of itself, this is given to you. From this you can see what it will become. So it will become a comma e. Okay, so it will become a comma e. So finally subgroup generated by that will be a comma e. Okay, that's it. This will always happen. And what is the subgroup generated by e? What is the subgroup generated by e? That will be e. Okay, now interesting consequence of this question. Tell me. So G is a group which can be generated. Remember, G is a group which can be generated by A. G is a group which this group can be generated by A, which is inverse of itself. Which is inverse of itself. Then what can you say about order of G? See, very simple. This question, what this is saying, that you have a group. Okay, so some group you have, and in this group, the question is saying that A can generate G. What it means? What this is equal to? Tell me. What this is equal to? This element can generate G. Okay, this element can generate G, and it is given. This is given to you. This is given to you, and also it is given that it can generate A. It can generate G. What it means? It means this is equal to G, right? Yes or no? Because A can generate G, so I can say that this is equal to G because of this situation, because A can generate G. So this is very important. So from these two things, now you can notice that A generator of G. What it means? If I say A generator of G, this statement means that subgroup A can generate the complete G. Okay, this is the meaning. Subgroup generated by A is equal to G, and also A inverse is equal to A. What this means? This means what is the subgroup generated by A? That will be A comma E. So finally I can say that G is equal to A comma E. Finally I can say G is equal to A comma E. So okay, so I can say, remember A can be E also. So I can say order of G will be less than or equal to 2, or I can say that order of G will be 1 or 2. So how many such groups are possible? How many such non-isomorphic groups are possible? How many such non-isomorphic groups are possible? Okay, so like this question I can ask. So you have a group. Okay, this type of question I can ask. Let's assume you have a group. Okay, and such that A can generate the complete group. A is the generator of this group. Okay, such that A belongs to G. A can generate the complete group, and also A inverse is equal to A. Then how many such non-isomorphic groups are possible? How many such non-isomorphic groups possible? How many such non-isomorphic groups possible? The answer will be simply 2. Okay, the answer will be simply 2, because okay, group of order 1, either group of order 1. Okay, so how many group? Only one group you have. Group of order 1. And how many group of order 2? That is also 1. Okay, so this is the idea. Is this clear? So how many such non-isomorphic groups are possible? So the answer will be only 2. 2 non-isomorphic groups are possible. Group of order 1, order 2. You already know group of order 1, only one template. Group of order 2, only one template. So I can say that every such group is abelian. Can I say? Can I say that every such group is abelian? Yeah, right. Yes, bilkul. Okay, correct. So I can say every such group will be abelian. This implies abelian. So how many non-isomorphic groups are possible? 2, and each is abelian. Each is abelian. See, this is the question. In the question, you are saying that this A can generate the complete group. This A is the generator of G. It means G is equal to, this, and A is equal to A inverse. It means this. So from these two, I can say G is equal to A comma E. But A can be E. So I can say cardinality of group, that will be less than equal to 2. Because remember, G can be E also. This group also can be there. Or G can be like this. So these two groups are possible.